Hello, class. So on this video, we'll continue on the discussion we were having before about the three cases that we get from the roots of this characteristic polynomial. So if you remember in the previous videos, we already saw the first two cases. We get the case in which we get two real distinct roots, in which case this is the general solution, right? Where R1 and R2 are the real distinct roots. In the case that we get one real root of multiplicity 2, we had to use the reduction of order theorem, or theorem 1, to get another solution. Right? And we found that the other solution was basically the same thing, just add an x in front. So in this case, the general solution was, that we have here, right, c1 e to the rx plus c2 x e to the rx, where r is the unique real root of multiplicity 2 that we found from the characteristic polynomial. And of course, as always, c1 and c2 are arbitrary. Now we have one last case, the case in which we have two distinct roots, the problem being that they have an imaginary part. So first, let's see what this case looks like. Right? So again, let's write what the two solutions are from the quadratic formula. And I'm not going to write them as R1 and R2 right now. I'm just going to write it as one variable, but we get the two roots because of the plus or minus. Negative b plus or minus square root of b squared minus 4ac over 2a. Now, what is necessary for us to get two distinct roots with imaginary parts? Well, the imaginary part is going to come from what's inside the square root. Basically, if you're taking the square root of something that's less than 0, you get an imaginary part. So for example, let me just remind you a little bit how it works. Let's say you want to take the square root of negative 3. Well, we can't do that in the real plane, right? Because we can only work with non-negative numbers. What you do instead is that you rewrite or use basically the property that I squared equals negative 1. So basically what are we doing here? We're introducing a new variable, which we're calling I, with the property that I squared equals negative 1. So the idea is that when you write something like this, and now here you have to be a little bit careful. What we can conclude from here is that we're going to let the square root of negative 1 be equal to I. Now you have to be careful with how this works in the complex plane, because the square root function, there's actually infinitely many of them that you can define in the complex plane. So things get very weird. But for our purposes, all you need to know is that we're going to be working with this identity here. Again, this comes from this first identity, that I squared equals negative 1, and again, some choice of things that happen in the complex plane, but don't worry too much about that. How you want to think about this, though, is that whenever you have the square root of something negative, you can think of this as being square root of negative 1 times the square root of 3. All right, so you basically split the square root into the negative part and the positive part. And then the square root of negative 1 is I, right? So this becomes square root of 3 times I on the outside of the square root. Right, so that's the idea. So anytime you have something negative inside, you take the negative 1 outside, rewrite the square root of negative 1 as I, and you just leave the positive part inside the square root. Okay? So us having an imaginary part, right, and anything that has something like this, so we would call an imaginary part. Right? So for us to have an imaginary part, it's equivalent for us, or for b squared minus 4ac to be less than 0, right? Because that's what is inside the square root. Okay? So just something to note, that just as a reminder, that's when you would get an imaginary part. So in general, after you simplify all this, right, so you know you're going to get an imaginary part in your solutions because b squared minus 4ac is less than 0. You're going to get two solutions after you simplify, and they're going to look like R1 equals some real number plus, actually let me not use a because I'm using that already in the original characteristic polynomial. So let's use alpha plus beta I and alpha minus beta I. Oops. I. Where alpha and beta, right, so alpha minus 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 b are real numbers. Right? So anytime you start with something like this, and you're going to have an imaginary part, you can simplify that to look like this. There's some real part alpha plus some real part beta times I. And then, of course, we get to solutions of the minus sign. So we get another solution, alpha minus beta I. Right? And it's always that. These are always the two solutions you get. So the two solutions we get from this for the differential equation, not the quadratic formula, would be then y1 equals e to the alpha plus beta I times x, right? That would be one of them. And y2 equals e to the alpha minus beta I times x. Now, why is this a problem? In this class, we want to focus and stay on the real plane, right? So the xy plane. However, when we plug in values of x, we have an I in both terms here, in both solutions. So these functions actually map to the complex plane. And again, we don't want to worry about the complex plane. As of now, not because it's not useful, it's actually very useful. It's better to work in the complex plane than in the real plane for a lot of things. However, we haven't studied the complex plane, or at least it is something that I can't assume that we've done. So what do? We don't want to have solutions that map to the complex plane. We want to stay in the real xy plane. So there's actually a trick we can do here. I'm not going to do all the work because it doesn't take that much time, but I don't think it's that intuitive. I might ask you to do some of it as an exercise in the homework, but the idea is we have these two solutions, and if we use or using something called Euler's formula, and don't worry about this about what this is. You can see in the book they do the argument about how they use Euler's formula and what Euler's formula is. For our purposes, doesn't really matter because what we're really interested in is finding two linearly independent solutions that map to the xy plane. In this case, I'm not really that interested in how we get there from these two solutions that map to the complex plane. But the idea is that they use Euler's formula and they also use the superposition principle, right? So remember, the superposition principle is what we're using, or what we saw before, what we're using now, that given any number of solutions to a differential equation, any linear combination of them are also solutions to a differential equation on whatever common interval of definition you have. Right? So that's what the superposition principle is. And again, if you're really interested about how they do this, you can look it up in the book. Again, it's either section 3.3 or 3.4. Oh, superposition principle. So basically, it's using these two things. What you can do is, from these two solutions, you can derive two other solutions. So what are these two other solutions? They're going to be y1 equals e to the alpha x, and I should have seen. I guess the order doesn't matter, so I'm just going to write cosine first. Cosine of beta x, and you get another solution, y2 equals e to the alpha x sine of beta x. And again, don't worry about this too much, how we get from, these two solutions that are in the complex plane to these two solutions. Only worry about the fact that it's possible, right? And again, if you're interested, you can look in the book, but it's not something I'm going to test you over. Now, why are these two solutions better? Well, if you notice, now everything is real, right? E to the alpha x times cosine beta x, since alpha and beta are real, right, we assume that, then this function maps to the real axis, right? So it's a function that spits out real numbers. That's what we want. We only want to work with real numbers. Same for y2. Right? E to the alpha x times sine beta x, since alpha and beta are real, this function is giving you real values when you plug in values for x. Not only that, I'm not going to prove it again. You can verify this using the Wronskian, and I could show you, or I could ask you in the homework to do this, but it turns out that these functions, right, so these ones, so let me just write them again, and y2 equal to e to the alpha x times sine of beta x are or let me write it like this, have interval of definition. So they work as solutions on the whole real number line. And not only that, they're also linearly independent on the whole real number line. So what does that mean for us? Well, we have two linearly independent solutions to a second order homogeneous ODE. We have a fundamental set of solutions. We know what the general solution is then. So y1 and y2 form a fundamental set of solutions for the ODE for all real numbers. And hence, we know what the general solution is. So yeah, let's use black. So general solution to the ODE on, and this works again for all real numbers because these functions have interval of definition all real numbers and they're linearly independent for all real numbers, is given by a linear combination, any linear combination of these two functions. So C1 times e to the alpha x cosine of beta x plus C2 e to the alpha x sine of beta x. And this is the general solution. So now what have we done? In each of the three cases, right, no matter what types of roots we get, we know what the general solution is. Okay? So let me summarize. So case one, where we have two distinct real roots. R1 and R2, then the general solution is just this linear combination when R1 and R2 are the roots, and this works for all real numbers. Two, and we have one real root, multiplicity 2, and let's call it just R. So let's call it R. Again, no need to use R1 and R2 because there's only one. Then our general solution is C1 e to the Rx plus C2 x e to the Rx. And then finally, whenever we have two distinct roots with imaginary parts, so two distinct roots with imaginary parts, and let's call them, let's give them names, just so, because I know that it's something a little bit new, right? So remember that you can always write them like this, where alpha and beta are real. Right? Then what's the general solution? Well, the general solution is e to the alpha, so the real part, cosine of OC1, sorry, I don't want to forget the arbitrary constants, beta x, so the imaginary part, and I say imaginary part, but let me just call it the real part. So in terms of terminology, I think, if I remember correctly, this whole thing is called the imaginary part, right? Because there's an I, but really all we're interested in is in the beta, right? So the real part of that part, right? That's what goes inside the cosine, and then basically the same thing, but you replace cosine with sine. Now, again, this is the, and of course, I forgot to write, both of these, case 2 and case 3, also work for all real numbers. So on I equals negative infinity to infinity, and on I equals negative infinity to infinity. So this is a summary. Now we know exactly how to solve any second order homogeneous ODE with constant coefficients. It's just look at the characteristic polynomial, look at what case you're in. Depending on what case you're in, you know what the general solution is. So now we're going to do examples, right? Because all we've done is just derive this. So we're going to do examples of how to use it, but you'll see it's pretty easy. It's just finding the roots, basically, and then seeing what case you're in. Now, since we did all the work here, right, about how we get these solutions and showing that they're linearly independent, once we get to the examples, you don't actually have to show all that work again. All the work you need to show me is, this is the corresponding characteristic polynomial for this differential equation. These are the roots. Since these are the roots, this is the general solution. Right? That's it. That's all you need to show me. You don't have to derive everything again. We already know that there's solution, that this is a general solution. We know that it works for all real numbers, and we know that well, that's all we need to know. If you want, if I state to write the interval of definition, then you know what it is, right? It's negative infinity to infinity. Right? I'm telling you that that's what it is. You can verify it using the Wronskian, except for the third part. There's kind of a little bit that I skipped, but still, right? You should know that this is the case, that it works for all real numbers, and that's it. So what we're going to do in the next video is we're just going to do an example. I think an example one for each one, and then you'll see how easy it is. What we're going to do later is try to generalize this. So what happens if it's not homogeneous? What happens if we have a second order linear ODE with constant coefficients, but it's not homogeneous? We're going to see how to find the general solution in those cases as well.